So this is a question on phase space and statistical mechanics in which the Hamiltonian or energy is given like this is equal to mod of P plus mod of Q. So don't think about the dimensions. Suppose that one unit which is multiplied that takes care of the dimension. Okay. So they have asked that what is the probability density at Q? So first of all, if I want to draw the phase space, so uh, you have done such graphs in which suppose this is 4, 4 is equal to mod of y plus mod of x. So like this is PQ graph, this is PQ graph. So if I plot this, and they are saying that beyond E naught, uh, the microstates are not accessible. Okay, they are not accessible. So we don't have to go beyond energy E naught because that microstate is not accessible. So that is kind of constraint that is given. So if I plot it, so suppose I give you a graph to plot 4 is equal to mod of y plus mod of x. Okay, this is the graph. So what you will do, you will just make it like this, y and x. So suppose here x is positive, y is positive. So it will become y uh, at x is equal to 0. What you will get? You will get y is equal to 4. And what is the slope? Slope will be, so like at x greater than 0, and here y is also greater than 0. So our graph will be like this, y is equal to minus x plus 4, right? So you will get something like this. This will be the curve. And because modulus function in x is there, so you will get like this. And because modulus function of y is there, so it will be symmetric about x-axis also. So you will get something like this and this. And you can write all the equations as you have written, like here y is equal to minus of x plus 4. Okay, because this is what mod of y is equal to minus mod of x plus 4. This is the equation. So depending on in which quadrant you are there, suppose you are here, so x is also positive, y is also positive, so it will become y is equal to minus x plus 4. Here, because y is positive but x is negative, so what you are going to get is y is equal to x plus 4. Okay, so that's why curve is like this. So similarly, you can write equation here and here, you will get something like this. So similarly, if I plot it for E naught, because we don't have to go beyond E naught, so here also I am going to get it like this. This is the phase curve, and here you will get the P and Q. So here you will get this is equal to E naught, and here you will get minus E naught, and here E naught, and here minus E naught. Because what is this? Q is equal to 0. What is this? P is equal to 0. So similar curve, exactly same. So sometimes they test your knowledge of graphs or concept of modulus in phase space. So one basic concept is intermingled with one advanced concept. So clearly, if you see total area of the phase space, total area, that is E square. That is for sure, right? And for small probability, what I am going to do is I will divide the phase space area of a small phase space volume with the total phase space area. Okay, so let me write it. So I will write the small one is like this, dp dq, and divided by the total is E square. This will give me a small probability, the probability of being in that state. Okay, and if I write it in terms of one dimension, suppose I will write it in terms of p, it will become p dq by E square. Okay, so I am writing a small one, so just remove the integral, sorry, just a small probability. So p dq by E naught square. And they have asked for probability density, which will be dp by dq, and that is equal to p by, and what is p? P P dq. So dp by dq is, what is P? P is equal to, it is E naught minus Q, right? And it will become E naught minus Q by E naught square. So this is the probability density. Okay. So dp by dq gives the probability density of this, and this is the answer of that question. So you don't have to hesitate in applying the basic concept of mathematics, which you already know. Equations like this, if they appear for some uh, some Hamiltonian, you have to just treat them like that. Okay. Thank you.